So I want to talk to you about a package that's been around for about a year called Recipes. We're creating a new tidy models verse of tidyverse packages that are really specific to modeling. So Broom would be an example of that, Infer. And this is one that really is revolves around what you can do with your data, especially if you're going to take that data and put it into a model. So let's think about LM for a minute. Let's say we had a data set like the Ames housing data, which has become the new IRIS. So if you've seen it already today, or this week, sorry. Let's say we want to fit a linear model where we want to predict housing prices, which are fairly rate skewed. So maybe we want to log the housing price when it goes in the model. And then let's say we only had two predictors. One is a qualitative predictor that it's what kind of alley does the property have. And its values you can see are gravel or no alley access or paved. And then let's say we had another predictor that was just a lot area, which is just a numeric field in the data set. So if you're fitting like a standard LM model, you'd use the formula method. And basically what that formula method does, if you were to walk through the internals of LM, is the first thing it does, it says, well, let's take that data set and let's subset it on when it was sold. You can see the conditional logic there. And then the next thing it does is it creates a design matrix, which is the old school X matrix that goes into your model. And that design matrix would have a column for the intercept, and it would have the predictor columns. Even though we have two predictors, it would actually generate 3 additional columns. So it would have a column for the numeric lot area variable, but then the dummy variables that get created from the qualitative alley predictor would then have 2 levels because there's 3 levels of the factor. So then once it creates that design matrix, the next thing it does is it would log the Y data, the outcome, and then pump it into lm.fit, and that's what comes back. And so really what Recipes is designed to do is to make it sort of be like, model.matrix mashed up with dplyr kind of syntax to create your design matrix X. You can do a lot of things with Y or other types of variables. It doesn't have to be a predictor and outcome in Recipes, but the main motivation was what you can do with your predictors. So like I just said, we can take that description of the steps that are happening inside of LM and just write them down as like an algorithm or a workflow or something, right? So it's like a recipe. So it's something what we're saying what we want to do. Now the difference is when you run LM or model.matrix, you've mishmashed or you've combined the actual intent of what you want to do, the statement of we want to do these steps, with the actual doing of it. And that actually kind of prevents you from there's some more complicated things you might want to do, and that prevents you from doing those. So a lot of what Recipes was designed for was just my frustrations over the years with the formula method is fantastic, and it's one of the things I think that's made the S language so popular. But it does have its limitations in terms of things you might want to do that are not even fancy machine learning type stuff, but you'd like to do that in the variable specification. So what Recipes does, one of the things it does is it separates the idea of this is what I want to do from the actual let's do that part. So the basic, I'll call this a grammar, although I don't think I've done that until now, is the idea of how does this work? There's sort of 3 stages. The first stage is sort of the definition of what you want to do, like those steps that I just listed. And that would be done by the recipe function. So the recipe function, really all it does is declare which columns have different roles, like is this a predictor or an outcome, is it a strata or a censoring indicator. So that's one thing Recipes does. And the other thing is, as you'll see in a minute with steps, you can then list, well, here's the things I want to do with those variables in the data set. So if I want to center and scale them or log them or what have you. And that's, again, Recipes, all it does is it says this is what I want to do. Now, some of those steps are going to require some sort of estimation or some sort of calculation with the data. So if I'm centering and scaling my data, I need to calculate standard deviations and means for whatever columns I want to apply that method to. And so the second stage is sort of like what I call the estimation phase, sort of estimation in quotes, and that's done by the prep function or the prepare function. So what you're trying to do is you're trying to prepare a recipe. Like if you're in your kitchen, you know what you want to do. Now we're going to get together the vegetables and dice them up. We're not really making it yet, but we're just getting all the stuff together to make it. And so the prepare function is where you would then do any estimation bits that you need to do. And so then once you have that, you're really able to then project that sample or that pre-processing algorithm, that recipe, onto data sets. So up until recipe and prepare don't really do much in terms of applying it to data. And so like when you want to actually apply these steps and the things you've estimated for them, there's two different functions that you can use. One's called bake, and as you'll see in a little bit, bake you can run, you can execute your recipe on any data set you want to. Juice is a little bit more specialized because often in the process of making the recipe, doing the prep bit, you're actually applying those steps as you go. And a lot of times, if we have a data set that's not extremely large, you might want to retain that instead of redoing all those calculations on the data set you use to estimate them. You'll see that in a minute. So that's sort of like the apply phase. So here's what we can do. Let's load a couple packages. I'm going to take this data set, the Ames data set, and we'll just split it out into a training and test set, mostly just for illustration purposes, using the R-sample package. But in the process, I get this Ames underbar train and Ames underbar test. And so what we're going to do is we're going to have a small recipe that just takes sale price, logs it. It kind of emulates what I showed you in the LM fit. So the first little bit there is saying, when you give the data on the bottom left hand there, all the recipe package or the recipe function does is says, oh, which are the variables, what are their types, are they categorical, are they factors? So you don't even need to give it the entire data set. So once it parses all that and figures what you want to get out of that data, then you can add these step functions, which are the items in your list of things you want to do. So if I want to log the outcome, I can say, step log of sale price, and you can see the pipe is being used here. And then if I want to convert alley to dummy variables, I can just use step dummy. And so that kind of emulates, outside of the subset part, that kind of really emulates what we were doing originally in the LM fit. So, we have that recipe. I said prepare in the earlier slide. That actual function name is prep. So we want to prep the recipe. We need to give it the actual data set we want to do our computations on, or at least where we want to derive our calculations from. In this case, it would be the training set. So what the training set in this case would do, it's not really doing any estimation, but that's where it would figure out, okay, what are the levels of alley and how should I, what are their levels and their orders so I know what the encoding system is for dummy variables. But if I had like a centering and scaling bit here, prep would be taking those in the process and then be estimating everything it needs for it. So at that point, you've got a recipe, and I assigned it to a different name here, rack underbar trained, and now I have filled in all the blanks as to what are the things I need to estimate to apply this recipe. So there's another argument on here that says retain equal true, and what that does is I kind of wanted to keep that recipe object to be a small footprint. So if you have a very large data set, in the process of prepping that recipe, you're going to execute the step and then immediately apply that step's results to the data set. So when you get to the next step, you have what that data should be at any given point. So since you've already done those calculations for the training set, you can actually just save that so you don't have to re-execute it again. But you only save that if retain is equal to true. And I might default that to true later, but if you have a really big data set, then that could blow up the size of that recipe object for no other reason than it just saves the object. So then if you want to get the actual process values out, then again, if you want to get it just from the training set, you can use the juice function, and that just looks up that slot in the recipe object and says, yeah, return that data set to me. But if you want to apply those operations to a new data set, like the test set in this case, then you can run the bake command on the recipe and say new data equal to Ames test, and it would give you the results back that you're looking for. So the thing is, in this previous bit here on the bottom left, when we were specifying variables, I use their names. I didn't quote them because we don't really do that in the tidyverse. But the thing about recipes is, it's funny because you might have steps that create or eliminate variables that subsequent steps might want to use. So you might be running specifications for, I want to do this step, but I don't know the variable names or how many there are. So think about dummy variables. In this case, we kind of know what the dummy variable values are. So if we want to have subsequent steps access the dummy variable for a gravel alley, then we could hard code that and write it. But in doing this, I wanted to have more selectors than what dplyr gives you, like matches or contains or starts with. So I wanted to have selectors that were things like, hey, do this for all the predictors, or do this for all the numeric data. And so what we've done is we have a different set of selectors. So let's say you do feature extraction, and the way recipes does it is it gives those new variables the prefix PC. So if you have a step after that, you might say, well, give me the number of components that gives me 95% of the original variation. And that might be 10 or 20. You don't know. So, one question is, how would I write a step after that if I don't know what those variable names are? And so you can use either dplyr selectors like starts with to get there, or you can say, well, do that on all the numeric columns, but not on the outcome because I want to process my predictors. So we have these all functions that are for the data type, whether it's numeric or nominal, whether it's a predictor or an outcome or the censoring variable and so on. And you can use them in combination. And also when you're trying to get your data back from juice or bake, you can use those selectors after the fact. By default, it just gives you everything back. But if you're going to predict a new data set, that data set doesn't have the outcome. So, if you go to get that, it might say, well, I don't know where the outcome is. Instead of running juice on everything, you can just run it on the all underbar predictors to just get the ones back that you want. It might be on another slide, but there's also another option here. If you want it back, it comes back as a tibble, but if you want it in a data frame or a matrix or a sparse matrix, you can, when you bake and juice, you can specify what format you want. So another nice thing that you can't get from the regular formula method is, if you have like 15 models that you're fitting and they all use the formula method, you're redoing those formula computations every time. And so we wanted recipes to be reusable. So let's say I take my recipe that's already been trained and I want to add some new steps to it. So now when I go to prep that, you can see it shows up here at the bottom. It doesn't redo any computations it doesn't need to. And so then, like if you have some like let's say you want to do some fancy autoencoder, but you're not sure if you really want to do that for all the data, you can have a variation of your original recipe that does that autoencoder, which doesn't need to then redo all the things that came before it. And then maybe from there you decide, well, I really ought to log this one variable. You can add another step with having to redo that, that autoencoder that took 10 minutes to fit. So you can recycle things as much as you can. So here's like the laundry list that's, I'm going to start splitting this off into different packages because it's becoming a little bit unmanageable. But there's a lot of things like, basic things you would want to do like logs and square roots and that sort of thing. There's a lot about encoding. So, I have a lot of data sets where you have a factor predictor that has thousands of values. And some of those values might only be measured once or twice in the data set. So in Ames housing data, there's like a neighborhood factor. And North Ames has a lot of properties in it, but there's one property in this neighborhood called Landmark. And so, if you're resampling and things like that, you might end up not getting that in the training or either in the training or test set. And so, a step you might want to do is say, well, if I have really low frequency data in the training set, redefine my factor level for that variable to have a category that gets pulled, any rarely occurring levels then get pulled into other. There's other things you can do a lot with ordinal predictors and things like that. There's a tons of statistical calculations like different variations of PCA and dimension reduction bits you can do here, and splines and all this stuff. There's a lot of imputation methods. There's not as many as I want to have, but this is another good example. Like you can do inline things in the formula method, but if you want to impute a particular variable, it's possible that you could write an imputation step that you could use inline in model.matrix. But then if it's a model-based imputation, the terms object has got to save this potentially large model object. And you would have to do that inline separately for all your predictors. So it's really easy to say step impute, whichever method you want to use, and then have it store that in a much more reasonable and usable way. There's a lot of package vignettes about this on the package down site, and there's something else I was going to say about that, but it's gone. So here's a more complex recipe that we might use for the Ames data. So you've seen a lot of this so far. We take neighborhood and we collapse it there by saying, if in the training set I have any variables or any factor levels that are less than, let's say, 5% of the total data set, take those and pull them into other. And then after that, you can do your dummy variables. So order matters here. So if I create the dummy variables before that step, neighborhood, that actual variable doesn't exist anymore. So caret has a much more simplistic preprocessor in it, but those steps are fixed because we decided just to stop errors like that, we need to fix them. But recipes, you do have the ability to shoot yourself in the foot, so have at it. Make sure you send a GitHub issue about it later. So you can create dummy variables. based on any nominal predictors that are there. Interactions were a little bit weird to encode here, so that's the one place where the API is a little bit different. You have to use a tilde to specify the interaction, so you can have like, A colon B plus C colon D. Another thing you can do here is if you have dummy variables that get created, you can use a selector in the actual interaction definition. So again, if I wanted to have an interaction with neighborhood and I did step other, I don't actually know which variables are going to be around later when I want to do this interaction. They're dummy variables. And so I can do like a starts with neighborhood colon and then some variable to make sure I get whichever interactions exist at that point in the recipe. And then you can do things like, basis functions like splines and things like that as you might want to. So with the tidy modeling sort of framework we're setting up, we're writing the foundational parts like resampling and recipes and things like that. And we will hopefully soon get to higher level APIs so you can use this and not have to worry writing like a tons of per map commands, which is fine. I mean, we can do that and we know how to do that. But right now, if you want more high level interface that uses recipes, I've been integrating it in with caret. So as an alternate method of doing like pre-processing, you can give train or some of the feature selection functions inputs as the recipe and the data set. And then it'll do things responsibly in the sense that we do a lot of resampling, and it's important that you re-estimate or re-prep the recipe within each resample. It would be a really potentially bad idea to prep your data and then put it into some resampling-based modeling situation because the resampling doesn't know about any of those computations you did. So if you have like an imputation method you're using that has a lot of instability in its estimation process, you'd want that instability to be reflected inside the resampling statistics, probably negatively because it's unstable. And if you do that prior to showing it to train, it doesn't know that that exists. So you would probably be more optimistic about what the performance is. So it's a little more computationally intensive, but it's the right thing to do to include that recipe's re-estimation every time you have a different data set during resampling. Yeah, in the feature selection bits, I'm actually working out. Hopefully on the plane ride home, I'll have worked out the final parts of it. So it would be nice to be able to do that with the recursive feature elimination or the genetic algorithm methods and things like that. So future plans is what I want to do is I want to add more steps. I have some steps that are like specifically use like TensorFlow or Stan, so I tend to like segregate those in different packages so that recipes proper doesn't have like tons and tons of dependencies. So we're doing that. Some people have been writing other packages to use it. Now, one thing I want to do is instead of having like step log, step square root, and things like that, I don't think, I haven't done it yet, so we'll see if this is true, but I don't think it would be difficult to have like dplyr verbs in there, like mutate or filter. So you could have like step mutate and then give it, what you would have given to dplyr as mutate, and it just treats that as another step and executes those in the process of the recipe. So that would give a lot more flexibility, and it would obviate the need for a lot of the low-level steps that are there. Tidy models, this integrates really well with RSample and some other things, but as we write more framework packages, you don't have to use recipes, but it has some advantages to using it, so we'll just keep integrating it in there. And then one thing that's kind of like, I don't know, I think it's going to be doable, but maybe I shouldn't say it on camera, is, we get grief sometimes with R, it's like not high performance and things like that. And so, the nice thing about TensorFlow is TensorFlow is a really low-level language. So it creates this graph of computations. So if you're adding two things together, there's like a plus operator, and then two variables go into that graph. So symbolically, it would not be hard to write exporters for prediction functions or recipes. So if you have like a recipe that then gets fed into LM, writing the TensorFlow graph for the LM, prediction function is actually pretty trivial. But then since it's symbolic, any pre-processing we did to like X1, we could refer back to the recipe and any estimation bits we had there and write the symbols for that. So we can have this like nested way of exporting that prediction function from the original raw data to whatever the model used and export that to a TensorFlow graph that could be used in whatever Plumber or whatever API that you might be interested in. So it might really enable like really high performant predictions from data sets. So that's where it's going, and again, I haven't not done a single thing. There are people in RStudio who could probably do this, and I keep like dangling it in front of them, hoping they're going to want to jump ship and work with me on that. But anyway, so that's one area that we're going. So that's it. Thanks.
Thanks, Max. Since Max is last, he can basically do whatever he wants, but we're
Later.
pretty much we're on schedule, so we certainly have time for a couple of questions before lunch. Miles?
So he was asking about the dependency relationship between caret and recipes. So is caret? I don't think caret is like a depends or an imports for recipes. Oh, okay. It's my goal to not do that. I mean, caret has tons and tons of dependencies, and I want to reduce that down. So yeah. So caret uses recipes as imports, and I don't want that to be the other way around. I'm trying to have to figure out why that is, because I don't want that. I mean, there's a lot in there. So, for example, like the Yao-Johnson transformation is like a better version of the Box-Cox transformation, and I made a point of writing that from scratch instead of just re-importing what caret gives you. So I definitely want to get rid of that and have it be as small as possible. Yes? Yeah, so the question is, do I intend this to replace formulas? No. I mean, that's like a atomic part of the S language. I would like to use it as an alternative because, if you have like, y tilde, x1 plus x2 plus x3, like, use the formula. Like, you don't have to use this. There's like more typing involved here. But at the same time, my preference would be models to have a formula interface and a non-formula interface and a recipes interface. But, those first two don't even exist for many model functions because, so there's like a whole other manifesto we're writing about like how you create a modeling package. So, so my intent would be to have, I'm also working on another package that basically can be used as a wrapper. So if your underlying, shouldn't be surprised anybody. So if your underlying model that you want to use it with recipes, but it only has a formula method, we'll have something where you could use the formula or non-formula or recipes interface to then use that model and so on. So, I'm not trying to eliminate anything from R, really, but hopefully, without getting into like really complicated machine learning stuff, there's some really interesting things that would just be impossible to do without like a recipe or something like that. One final note about that is I haven't really gotten to many examples of this, but I've just been showing examples of where your data have predictors and outcomes. But there are many other roles that variables could take. So you might have a strata variable, and that's not necessarily something that's a predictor. Or like you might have data in your column that you need to use to estimate performance. So like you're predicting, let's say, the probability somebody's going to pay back a loan. Your objective function that your boss doesn't come to you and say, give me a model with the lowest root mean squared error. He's saying like, she's saying like, give me a model that optimizes the expected profit from a loan. And so you might have variables in your data set you need to come along with any resampling or anything else or any pre-processing methods that aren't in X or Y. And so recipes is good at that is you can define on the fly your own sort of roles of variables. And so there are some, for example, modeling functions that have predictors that are used for only splitting in trees, but then other predictors that are used in models within the tree nodes, and those have different roles. So I think what recipes gives you is actually an even richer set of things that you can do than the formula method would, because the formula method would have to be sort of rewritten or a new package that adapts the formula method for all those different types of different roles. And this just kind of does it for you because it's not using any of that machinery. Yes?
So, are there any unexpected effects when you use recipes and prose to using the traditional model? One thing that comes to mind is how it's handling factors, and it seems to be doing what I'm encoding on now, that you get potentially different results out of
So the question is, are there any unexpected effects? And specifically, like your question was about, like, encoding categorical predictors and dummy variables. I mean, there are, and partly because you can do things in any order you want. So we're rewriting another book, and we have a good example where there's a really significant interaction in this one data set. And the model we're going to put that in requires centering and scaling. So we can, I can't remember the order offhand, but if you center and scale the predictors before putting them in the interaction, I think in that case, you get the interaction being significant. But if you compute the interaction and then center and scale, the interaction goes away. Right? So there are things I never thought about that now we have you can do that. Martin's shaking his head like, there's a lot of things that you can do here that we never really had to think about. For encoding the categorical variables, it doesn't do one hot by default. So we just, in the last version, added an option for that because people, if they're putting something in GlimNet, they're okay with that linear dependency and they wanted to get all the dummy variables. So I don't think, I took a lot of care about that because model.matrix does some weird things because you would think if you just gave it a formula with an interaction, it would give you one thing, but you actually get different variables from those interaction columns, whether you put the main effects in and the interaction versus just the interaction in a formula. So there were things just in the formula method, I'm like, no, that shouldn't do that. And so then we had to sort of figure out how to make that work. So if there are things that surprise you, let me know, just because that wouldn't astonish me that would happen, and that might be an artifact of how we do recipes. But in a lot of cases, it's just the fact of, like, for example, let's say you center and scale your data and then do a Box-Cox transformation. Box-Cox transformation requires all your data to be greater than 0, but you've just centered the data. So there are situations where you could, like, mishmash things up in a way that just doesn't work. Yeah.
All right, I'd like us to, thank all of our speakers.